Okay, so last week we talked about the design of filter, we have talked about the FIR filter, IIR filters, so a lot of things we have talked about. So this week we talk about the linear prediction and optimum linear filter. So why we design the filter? If you see that we have talked about the filter design, why we design the filter? So the design of the filter design perform for signal estimation. So using the filter design, suppose I want to see whether the from 1 kilohertz to 2 kilohertz the signal frequency component exists or not, or estimate the signal within this frequency range. So estimation of a signal, we definitely use the filter, and in many applications like that I have said, communication system, control system, geophysics, and many others application and discipline, we use the filter as a performance signal estimation. So if you see, when I say the low pass filter, when I say band pass filter, so this estimation of that signal, the design of that filter is based on the approximation of the ideal response of a low pass filter, high pass filter, band pass filter. That is what? Now suppose I said in communication system, I want to estimate the signal, estimate the spectral content of the signal in between, let us say 2 kilohertz to 4 kilohertz. When I say that, that means I want to estimate the signal from 2 kilohertz to 4 kilohertz. Okay. So in that case, I have to design the filter. How do I design the filter? We consider a low pass ideal filter and then try to approximate that approximation, that ideal frequency response of the desired filter. So what are the design problem involves? Now this kind of design problem involves many constants. What are the constants? You know the pass band edge frequency, stop band edge frequency, pass band ripple, stop band ripple, pass band attenuation, all kinds of design constants are there. But in many applications, I required a filter that produce a particular deterministic frequency response, or perhaps empirically measure the power spectral density function of a random process. So I do not want that kind of constant kind of things. So what I do, let's say I want to estimate the power spectral density of a particular frequency range. So instead of designing an ideal filter using approximation methods, let's I change that topic to a modeling technique. So modeling means when you design a filter, what we are basically doing, from the desired frequency response, we try approximating the desired frequency response and find out the filter coefficient. Let's that we do not want that constraint methods. We want a modeling based approach. Can I design a filter using modeling? So what kind of modeling? Now what is a filter? If you see, what is a filter? Filter is nothing but a transfer function Hs, which is Bz by Ez. So Bz is the pole position, Bz is the zero position, and Az is the pole position. Now let's say there is three types of model. What are the model? Moving average model, MA model. MA. What is MA? MA is nothing but a when Hz is equal to Bz. Because if Hz is equal to Bz, then I know Hz is equal to summation of k equal to 0 to q bk z to the power minus k. Only zeros are there, no poles. So when we multiply with output, when I say I have a filter which is Hz, Hz is equal to Bz, if I apply a signal inside here, what I get outside is nothing but a multiplying a signal. So I can say Yz is equal to Hz multiplied by Xz, or I can say Yn is equal to nothing but a summation of k equal to 0 to q bk into z to the power minus k x of z, which is nothing but a, I can say z to the power x minus n minus k. So from the previous q number of sample, I doing a moving average multiplying by a constant bk, coefficient bk. So that's why it is called moving average filter. That means suppose I have a signal x of n, so I can say that 1, 2, 3, 4, let's say this is my x of n. Okay. So I said that I have applied a filter, so I can say that y of n is nothing but a moving average of, let's say, 3 number of sample. So 1 plus 2 plus 3, with a multiplication of 1 will be multiplied by the b1 or b0, b1, b2, and then sum them. Then I can say 2, 3, 4 sum, then 3, 4 let sum. So it is a moving average kind of things. That's why it is called moving average model. Then autoregressive model, autoregression model. What is autoregressive model? Hz is equal to g by az. So I said Hz is equal to g by az. So my Hz is equal to g by az. G is the gain. Az is nothing but a k equal to 1 plus k equal to 1 to q ak z to the power minus k. Okay. So when I apply a signal x of n, x of z, I can say y of z is equal to nothing but a 1 by 1 plus k equal to 1 to q ak z to the power minus k into x of z. So I can say it is nothing but a y z plus k equal to 1 to q ak z to the power minus k into yz is equal to xz. Now when I say time domain signal, so it is nothing but a y of n is equal to minus k equal to 1 to q ak y of n minus k plus x of n. So when I want to implement it, so I can say there is a feedback, negative feedback, that y of n will be delayed by z to the power minus 1 or minus 2 minus 3 minus k and feeded to here, negative feedback. If it is plus, if it is minus, let us say it is minus, then I can say it is nothing but a plus. So I can say it is feedback, positive, let us say positive feedback. So I say that current sample y of n depend on the previous current output, depend on the previous q number of output plus present input. So it is called auto-regressive method. That's why it is written as Hz equal to g by az. So it only has a pole, no zero. Now there is a auto-regressive and moving average model of ARMA model, ARMA model, which has pole 0 both. So I can design a rough filter by using some modeling technique. Instead of constant specification of the filter, I can some modeling technique and I can design that filter. For example, suppose I said I have given you a signal which is look like there is some variation, local variation is there in the signal. I want to remove this local variation. What I do? I can say, okay, local variation can be do by modeling a moving average filter, which is nothing but a low pass filter. So I want to smooth that variation, which is nothing but a low pass filter. So instead of designing low pass filter, providing omega p, omega s and all kind of constant, I just say the moving average model and I just implement the moving average model and smooth the signal. So when I say that in a random process, if I want to find out the estimation of the frequency, many times we use the modeling. So linear prediction is such kinds of a modeling example. So what is linear prediction? Forget about optimum filter design, linear prediction. Forget about the slides. So what is a linear prediction? So what is prediction? Prediction means based on the previous data, I can predict the present data, weather forecasting. Based on the past experience, the condition of the past experience can predict what will be happen if this condition perceived in future. So that is prediction. So suppose I have a signal x of n, let's x of n 1, 2, 3, 4, 5, like that. Now, can I say that I want to predict this sample from the previous two samples? How I want to predict? Now, this prediction is not non-linear. When I say prediction is there is neural network, is also a prediction, but it is a non-linear. Here I said linear prediction. That means I said this 3 is a linear combination of the previous two samples. Similarly, 4 is a linear combination of the previous two samples. 5 is a linear combination of the previous two samples. So, I can predict the present sample from the future sample. So, prediction, or I can give an example. So, why this linear prediction is possible, linear combination prediction is possible? Because you know, let us say this is a straight line. So, if I know this point, this point, this point, this point, or if I know the point, I can draw the straight line and I can predict the any point in the straight line from the previous point. So, I can say, let us say I want to predict x of n from the previous p number of sample. So, I can say x of n is a linear combination of previous p number of sample, maybe that a0 into x0 plus a1 into x of n minus 1 plus a2 into x of n minus 2, like that. Or let us say 0 I not consider, let us say 1, k is varies from 1, a1 x of n minus. So, from the previous sample I am predicting the current sample. So, it is a linear combination and a1, a2 is the coefficient. So, how do I estimate the coefficient? So, when I say my prediction is correct, so that is why I said the design of an optimum filter for a linear prediction. So, once I say it is a linear prediction, it also a filter. I said the current sample yn is a combination of previous few sample. Let us say k equal to 1 to p ak z to the power minus k minus y n minus k instead of time domain. So, previous k p number of sample I want to take the predict current sample. So, if I say that, then it is a transfer function will be nothing but a yz is equal to k equal to 1 to p ak z to the power minus k yz. So, I can say if I take this side, so it is yz is nothing but a 1 minus this one, and so when I say transfer function, it is nothing but a 1 by this z. So, it is nothing but an autoregressive model. So, let us say this is my system which is called linear predictor Hz. Hz is a system which is the linear predictor. If I give an xn as an input, I can get an yn is an output. Okay. Now, I said the purpose for this prediction is to predict current sample from the previous experiment, previous experience. So, if I say that I apply xn and I produce yn, so I can say yz is equal to hz into xz. So, what is hz? A by this one. So, I can say yz az is equal to g into xz. Let us there is a no input is there. No input is there. Then I can say yz az is equal to 0, or I can if I put it here az value of az 1 minus k. So, I can say yn. So, I put the value of hz in here. Okay. Then once I get this one, this is the yn. So, yn is equal to linear combination of the previous p number of sample plus current input. Let us the current input is 0. Then I can say the current sample yn is nothing but a linear combination of the previous sample. So, yn is equal to a1 yn minus 1 a2 yn minus 2 plus dot dot ap minus n minus p. This is a linear equation. Y equal to ax plus b is a linear equation. So, that is why I can say that linear yn can be predicted or yn can be generated from the linear combination of the previous input. Okay, I know. But if you see, this is a single equation and there is a p number of unknown a1, a2, sample I know, yn minus 1 I know, yn minus 2 I know, yn minus p I know, but I do not know a1, a2, ap. Let us say, give an example, let us say I said 3 is a combination of, let us say, or 4 is a combination of a into 3 plus b into 4, let us say. Sorry, a into 3 plus b into 2, let us say, b into 2. So, previous 2 sample. 4 is a combination of the previous 2 sample, a into 3 plus b into 2. Now, what should be the value of a and b? If I want to find out the value of a and b, I require 2 unknown, I require at least 2 equations. But here is only one equation. So, there is an infinite set of a, b solution is possible. A and b can be infinite set of solution. Let us say a equal to 4 by 3 and b equal to 0 can be a solution, or a equal to 0, b equal to 4 by 2, that can be a solution, a equal to something fraction. So, many solution is possible. Then how do I compute this a1, a2, ap? So, if I say, let us say a1, ap is an initial value and I calculate predicted value y of n cap, which is predicted value. Then what is the error? So, I know present yn minus predicted yn, that is my error. So, I can minimize that error. So, I want to choose those coefficients which give me the minimum error. So, the coefficient of the linear prediction filter A1 to AP can be find out by minimizing the prediction error. So, that is why it is written like this. The filter constant to be linear and the optimization criteria is based on the minimize the mean square error. And A1, A2 is nothing but a filter coefficient. So, instead of providing omega p, omega s, epsilon, delta, all those things, pass band edge frequency, stop band edge frequency, refill, transition bandwidth, instead of doing that, can I predicted, if I say my system is a linear system, that means I can, the present output can be predicted linearly from the past output, then can I find out the filter coefficient using estimation theory from the data? That is called modeling. So, when I say auto-regressive modeling, I use for linear prediction. Okay. So, what is my, well, in case of linear prediction, what is the problem? The problem statement is, I am estimating the present sample from the previous p number of sample, linear combination of p number of sample with a multiplication coefficient alpha k. So, alpha k is my predicted coefficient with a linear combination of the previous output, I get the present output. Okay. So, I can say yn if the predicted signal, then pz, this one is a prediction filter which is nothing but an FIR filter. It is nothing but an FIR filter. Summation of all previous, combination of all previous sample. So it is a moving average filter or FIR filter. So if I say what is the prediction error? En is the current sample minus estimated sample. So I can say Yn minus this one is the prediction error. So if I told you draw the prediction error system diagram. So I put an Yn as an input, pass through the Pz. Pz is nothing but an estimator which is estimated or predicted that Yn from the previous sample. Then I know Yn, I subtract them, I get the prediction error. Is it clear? So prediction error is nothing but a original value minus predicted value. So predicted value is this one, original value is Y1. So I can say that if Pz is a prediction filter which is the linear combination of the previous output, then Yn minus estimated signal is my error. Okay, no problem. Then Yn minus this one is my error, I know. Okay, so now if I take the Z transform of this equation, let us take the Z transform. So I can say Ez is equal to Yz minus k equal to 1 to p alpha k z to the power minus k yz. So if I say Ez by Yz, Yz is the input, what I said, Yz is the input, Yz is the input, Pz is the prediction error filter. So I can say that Yz by Ez, which is nothing but my transfer function Az. So I said I design Az, apply input Yn, I get that output is the error, mean square error. Output is the error. So Ez by Yz is nothing but a, so I can say Ez by Yz, which is nothing but a 1 minus k equal to 1 to p alpha k z to the power minus k yz. Okay, Az I know. So if I apply an signal and Az is in my estimator or error estimator transfer function, then output is my the error. Error. Now if I say what is 1 by Az? 1 by Az is nothing but a Yz by Ez. One by Az is nothing but a 1 by Az is nothing but inverse of Az, which is nothing but a 1 by 1 minus Pz. This is Pz. Now if I say, if I input is my error En and this is 1 by Az, I should get Yz. Or I should get Az, I should get Yn. So if I apply an estimated error through a 1, because it is a linear filter, so 1 by Az is also valid. So 1 by Az I can get Yn back. So what is the application? What is the application of this linear prediction filter? Let us say speech signal. So if you see, when I say the speech signal, if you remember that what is a speech signal? Let us give an example for speech signal. What is a speech signal? Now when I say speech signal, speech is produced by a human vocal tract. So what is human vocal tract constant? So this is a, let us say this is a throat, this is the dental part, this is the upper palate, this is the lower palate, tongue, and then this kind of systems are there. This is called velum and this is called nasal passage, this is nasal passage, this is oral passage, this is teeth, and then there is a velum will be closed, also there is velum, either velum will be closed or velum will be, so either the velum will be closed, so velum is here, so So velum will may be closed or may be open, the nasal passage, and then it is goes there and there will be a vocal cords. Here there will be a vocal cords. So this is the tongue. Okay. So our tongue is fixed at back side, some front side is open. When I produce a sound, this vocal cords is nothing but a membrane. If you see sani, in the head there is a membrane. So membrane will create vibration, and when that vibration pass through a tube, depending on the tube transfer function, that vibration characteristics will be changed. So what we will do during the production of the speech, we move our tongue in different position to produce different speech sound. So when I produce different speech sound, that means the different speech sound is only characterized by the transfer function of the vocal tract. The transfer function of the vocal tract, if it is HZ, so HZ is responsible for producing the different side sound, and for different sound HZ is different, and this is nothing but an excitation which is nothing but an source. So that's why when I say human speech production system is nothing but a source filter model. So this is called HZ, which is vocal tract, and this is excitation, which is nothing but a EN, impulse. Excitation is nothing but an impulse or glottal impulse. We call glottal impulse. So it is written as UGN. So this produce that impulse. So this produce an impulse. That impulse passes through a filter and produce speech signal SN. Now it is shown that it can be, when we derive the transfer function of the vocal tract, it is shown that yes, linear prediction is possible. It is in the form of G by AZ. When I producing the tube modeling of the vocal tract, it is nothing but a G by AZ. For details, you can go through my YouTube video. So the course name is Introduction to Speech Processing, where this is derived. Okay, so G by AZ. So I can say the linear prediction of the speech is possible. So what is the meaning? The meaning is that if I know the speech sample, let us say speech sample is known for a particular time, speech samples are known, then I can say that any sample can be predicted from previous sample. Let us say any sample can be predicted from p number of previous sample. So I can say any sample S of n is a combination of k equal to 1 to p alpha k z to the power minus k, or I can say S of n minus k. So previous p number of sample, I can predict the current sample. So I can estimate those alpha k. I know current sample, I know previous sample. So I can apply a theory which is called linear prediction theory to solve for alpha k. So once I know alpha k, that means alpha 1, alpha 2, alpha 3. So those are characterized this AZ. What it is meaning? That if I know alpha 1, alpha 2, alpha, so I can design AZ or I can design AZ. So once I design AZ, that means if this is my AZ, if I pass the speech signal SN in here, output I get EN, error. Error is nothing but a glottal impulse. Now if I design 1 by AZ and if I apply EN, I should get SN back, speech signal back. So when I say LPC analysis in case of speech, so there is two things. One is LPC analysis, one is called LPC synthesis. So what is LPC analysis? So when I say LPC analysis, that means I know the speech signal. This is my LPC analysis, LPC linear predictive analysis. So what is my purpose? My purpose is input is my Sn. I have to predicted this alpha 1, alpha 2 dot alpha k, that I can predicted alpha 1, alpha 2. So I have to compute those value. How do I compute that value? Minimizing the error. So I know Sn, I know Sn minus 1, I know Sn minus 2, I know Sn minus p. So previous p sample I know. So from those previous p sample, I will estimate another current speech signal and subtract it, get the error, and I am minimizing the error to estimate the value of alpha 1, alpha 2, alpha k. Let us say estimate. Then what I will do? I will design an error filter. I pass Sn using those alpha value, I get En. Error filter is the, so error signal is nothing but a Gödel excitation. Now this is LPC analysis. Now got for LPC synthesis. So what is LPC synthesis? In synthesis part, we will design 1 by AZ and we apply En excitation. I should get Sn, speech signal back. So where it is used? Now suppose I give an example. Suppose earlier, before the speech coding, have you heard about the speech coding? You heard about the speech coding. Before the speech coding is came, let us say I want to transmit a 1 second speech data from point A to point B. Now the speech is recorded with 16-bit encoding with 16 kilohertz, let us say. So 16-bit encoding with 16 kilohertz. So how much memory? So in 1 second, how much data is generated? 2 byte into 16k. So I can say 32 kilobyte is the generated data in 1 second. So if I want to transfer real time A to B, the minimum bandwidth is nothing but a 32 kilobyte per second. 32 kilobyte per second, that much of speed I required. Okay or not? So now that's why that when I say the voice over IP and telephone channel, when the telephone channel is discovered, voice over IP, today we can make a Skype meeting which is called voice going through IP. So there are two kinds of network. One is called IP network, one is called circuit switching. That means dedicated channel is created from the talker to the listeners, that is called circuit switching. But it is IP network, means packet switching. So in that case, I do not know how the packet will transport to A to B. But in case of telephone, there is a duplex communication between A to B. So if you are a communication student, you know that. Now voice over IP will be very cheap because it is shared by many people. But I cannot guarantee that this 32 kilobyte per second will be reached at B. Unless it is reached, I cannot real time communication is not possible. Then what is the drawback? They said, okay, why should I transmit 32 kilobyte? Am I not compress the data? So how do you compress it? Like the image compression. So voice compression is voice coding is come. So how do I compress it? So let us say in 1 second my frame rate is 100 frame per second. So that means I am analyzing 100 frame in a second. Okay. So for each frame I computing LPC coefficient, let us say. So let us say I am computing 20th order LPC coefficient. So 20, so P is equal to 20, let us say. And each of the coefficient alpha 1, alpha 2, alpha 3 can be coded at 4 byte. So how many memory required to store 20 coefficient? So 20 into 4, so I require 80 byte. Now instead of transmitting sample, so 10 millisecond, if I say 100 frame per second means each frame is 10 millisecond. So how much size if I transmit all sample of 10 millisecond? The size is 10 millisecond, how many sample will be there? If it is 16 kilohertz sampling rate, 160 samples will be there. Each sample is 2 byte. So total memory requirement is 160 into T. So 320 byte. So instead of transmitting 320 byte, I want to transmit only 80 byte. So I implement LPC analysis at the point A, extracted alpha 1 to alpha 20 and I transmitted those signal to B. Now in the B side, I will implement 1 by AZ. So I know alpha 1, alpha 20, so I can implement 1 by AZ and I can excited by a EN. What is EN? EN is a glottal excitation vibration, nothing but an impulse. So I excited that 1 by AZ by an impulse train, I get back my speech signal SN. That is LPC synthesis. So I get back my speech signal. So instead of transmitting 320 byte, I am transmitting only 80 byte. So that much of compression I receive. Now there is a lot of complication will be there. Then there is a F0, there will be a gain, there will be impulse position to make it more generalized or you can say more natural sounding voice at SN. There will be a lot of drawback due to this design. So those design constant can be improved by improving the size. Instead of only transmitting alpha 1, alpha 3, I can transmit along with the F0 value and along with the gain value and whether it is voiced or unvoiced. So I can get back all those information, I can design that LPC synthesis, I get back the data. So this is one of the use of linear prediction. There are many applications of linear prediction. So I can predict it. So instead of design a filter, I am predicting all. So filter is a transfer function, linear prediction is also a transfer function. So instead of specifying omega p, omega s, bandwidth, transition bandwidth, all those things, I am estimating certain coefficient value and based on that coefficient value, I am generating the signal again. So that's why it is called linear estimation. In next lecture, I will show you how to calculate alpha 1, alpha 2 and alpha values. Okay? Thank you.